The aim of this presentation is to be able to recall and apply the rules for assigning oxidation states in order to work out the oxidation state of an element in a compound or in an ion from its formula. So perhaps the first thing to appreciate is what oxidation states actually mean. So the oxidation state is a way of describing, if you like, the electron density within different substances. So relatively speaking, which of the atoms get the most electron density, or what are they worth, if you like. Now, if we have a look at some of the rules, the first thing that I would like you to do is to pause this and take some time to engage with the rules and work out what's going on and try to perhaps memorise some of these rules ready for a few moments' time. So pause the video clip and do that. Once you're ready, restart, please. Okay, so we're going to use these rules in order to assign oxidation states to different compounds, different atoms within different compounds and different substances. So let's start off with the first example here. So HNO3. Now looking at the rules, hydrogen usually has oxidation state of +1 like so. Just let me change this pen colour because it's not massively clear. Get a darker one, that might be better. So this one here should be +1. It's not a metal hydride, therefore that rule holds. Similarly, oxygen is usually in oxidation state -2. So hydrogen in the +1 oxidation state, oxygen in the -2 oxidation state, and the question is, what is the value for the nitrogen, because that's shown in purple. So I'm just going to give that a value of x, just like so. So if we use this example here, looking at the total charge, which is up here, is 0. So the 0 overall charge, we can use that to help us to work this out. So the hydrogen is +1, and the nitrogen oxidation state, which is X, and there are 3 lots of the oxygen, so 3 times by the -2 oxidation state is 0 overall charge. So let's work this one out then. +1 plus X minus 6 is 0. So X, that's the oxidation state of that nitrogen, must be +5. So we would say that this nitrogen atom here has got a +5 oxidation state. Let's do another example. This one's a bit more straightforward. Here we've just got phosphorus. It's elemental, it's not combined with any other atoms, and therefore this is an uncombined element with oxidation state 0. Let's have a look at this one. Now, usually oxygen would be in the -2 oxidation state, but this is one of the exceptions. It is in a compound with fluorine. Fluorine, however, always has an oxidation state of -1. So we can use that oxidation state to work out the oxidation state of oxygen. Again, in this example, there is 0 overall charge. And so we can work out as follows, that the oxidation state of oxygen added to 2 lots of the fluorine must be 0. So -1 times by 2 for the fluorines plus X for the oxygen equals 0. So -2 plus X is 0. Therefore, X must be equal to +2. So in this example, quite unusual, oxygen is in the +2 oxidation state. Notice that when we assign oxidation states, the oxidation state is for one specific atom within that substance. So here we would say that each fluorine has oxidation state -1. And there are 2 of those, so 2 times by -1 would go in the calculation, but we would still refer to the oxidation state of fluorine as being -1. Let's have a look at this example. This one's a little bit obscure. So here we've got 3 iodines all combined together, but there is an overall charge. So this is not an uncombined element. This is an example of an ion. So the overall charge is -1. So if we call the oxidation state of iodine in this particular ion X, we can then say, 3X equals -1. Therefore, X is equal to -1 over 3. So it is possible sometimes to get a fraction for an oxidation state, and that kind of makes sense here, because if this overall ion has charge -1 and it's got 3 identical iodine atoms present, so they would all have, for instance, exactly the same electronegativity, then it makes sense that that -1 charge is spread out over all three of those atoms, so -1 over 3 each. Let's look at the next one then. Now, sometimes it's important to think a little bit wider as a chemist to try to help work these things out. So overall, there's no charge on the compound here, but we could make use of perhaps what we know about the ions that make up this compound to help to work this one out. So this ion here is NH4 single plus, the ammonium ion, whereas this one here is NO3 single minus, the nitrate ion. So if we were to imagine that that's NH4 plus here and that's NO3 minus here, then that makes this question a little bit easier, because we can see that here we've got hydrogen, it's not a hydride, so that must be +1 each. If we call this nitrogen X, then X plus 4 lots of +1 equals +1 charge overall on that ammonium ion. So X plus 4 is +1, therefore X must be equal to -3. So the nitrogen at this side of this compound has oxidation state of -3. Interestingly, if we look at this side of the compound with the nitrate ion, let's call this one, I don't know, Y. Here then, each of these oxygens should be -2 each. So Y plus 3 lots of -2 is -1 altogether. So Y minus 6 is -1, therefore Y must be equal to +5. And that's what the oxidation state is over here. So interestingly, in this example, we've got the same element, but it has two different oxidation states all in one type of compound. Let's do one more example, and then you can go and have a go at some of these using the sheets provided. So in this example, we've got oxygen. This is not a peroxide, and it's not a compound where we've got fluorine, so we can safely say that that oxygen would be -2. Here we've got hydrogen. It's not a hydride, so we could pretty safely say that this would be +1. So we've got no overall charge overall, 0 overall charge. And so here goes 3 lots of +1 plus X plus 4 lots of -2 equals 0. So +3 plus X minus 8 is 0. So X must be equal to +5, which is why we would normally call this acid phosphoric 5 acid. Phosphoric 5 acid, like so, where this 5 refers to the +5 oxidation state of phosphorus within that acid. Okay, we've been through the rules, we've had a play with those, we've had a go at calculating some oxidation states. Go and have a go with some of the worksheet ones now, please.